So for me, are you ready?
You're up.
I'm
Your
gonna
team
stop
is up.
sharing.
Yeah, we're ready.
Okay.
All
I'm
right.
going to screen share.
So let me do a little intro.
Oh,
Excellent researchers all. What is notable for this one, and they'll get to it, is that not that many years ago, this was the stuff of science fiction. And I mean directly. And all of a sudden, given a paper that came out last year, we're talking about realities here. And I won't even bring up my buddy Avi Loeb. So with that, this is going to be a great presentation. I've heard it. Take it away, folks.
looking for Dyson candidates by Kwame, Sumeda, and Deepika. Defining the problem.
Carlos.
To explore the use
Oh,
of
Jaden.
supervised learning in determining the possible existence of Dyson objects in historical astronomical data sets by seeking exceptional values in the infrared portion of the electromagnetic
No.
spectrum. An extension of the search for extraterrestrial planets capable of supporting life as we know it.
Quick background. The question, are we alone in the universe, has fascinated people for centuries. There have been diverse efforts to find life beyond Earth, including the Search for Extraterrestrial Intelligence, or SETI, which tries to detect signals from advanced alien civilizations. Since 1992, we've discovered thousands of exoplanets, or planets orbiting other stars, and some of these could possibly host life. Additionally, projects like Breakthrough Listen Initiative use powerful radio telescopes to scan the skies for signs of intelligent life. And another interesting approach is looking for Dyson objects, which is the focus of our project. The concept of a Dyson object was first introduced in 1960 by the physicist Freeman Dyson in his paper, Search for Artificial Stellar Sources of Infrared Radiation. He proposed that a highly advanced civilization might construct massive structures around its star to capture much of its energy. While this concept is known as a Dyson sphere most popularly, the more accurate term is a Dyson object, which encompasses various theoretical designs and structures. So the concept of a Dyson object ties into the Kardashev scale, which was proposed by astronomer Nikolai Kardashev to classify civilizations based on how much energy they can harness. A Type 1 civilization can use all the available energy on its home planet. Type 2 can harness most or all energy from its star, and Type 3 harnesses energy on a galactic scale. Earth is often placed at around Type 0.7, but there is a lot of controversy surrounding this. We're still considered a Type 0 because we still primarily rely on non-renewable resources, and we haven't tapped into the full potential of the resources on our planet. So yeah, there's still a lot of discussion going on about this. And based on the Kardashev scale, Dyson objects fall under Type 2 because they're constructs that indicate a civilization which tried to harness the energy of its host star. And important signatures of Dyson objects include excess infrared radiation, because Dyson objects are, I guess, predicted to absorb and re-radiate its host star's light as infrared radiation. And then the irregular dimming of stars is also another signature. Here are some of the most common types of Dyson objects under discussion. So there's a Dyson swarm, which is a vast collection of independently orbiting satellites around a star, and this is the most probable type of Dyson object. And then there's a Dyson ring, which is a subtype of a Dyson swarm, but it's a single ring of structures orbiting in one plane around the star. And then there's a Dyson bubble, which is different from both a Dyson swarm and a Dyson ring because it's a shell of statites, which are kind of like satellites, but they're in a fixed position relative to the star. They don't orbit. And this is highly improbable because it takes a lot of structural integrity to overcome the forces of the star. And then there's a Dyson shell. This one's also impractical. It's a rigid sphere completely enclosing a star, and this idea is most common in science fiction.
So what is a Dyson candidate? A Dyson candidate is a star that exhibits unexplained light fluctuations without a steady pattern, like Tabby's star, which may be caused by a Dyson object, a sign of extraterrestrial life, obscuring our view.
So why is a search for Dyson objects and what we're doing important? The search for Dyson objects is important because it contributes to our search for life outside Earth. And searching for these megastructures connects directly to our quest to understand not just life on Earth, but the conditions necessary for life to thrive elsewhere. Additionally, Dyson objects are artificial constructs that would alter the light emitted by their host stars across multiple wavelengths, and the most noticeable change we expect to detect is an excess of infrared radiation, since the structure would absorb the star's light and re-radiate the energy as heat. This makes infrared astronomy and what we are doing in this project a very powerful tool in the search for advanced extraterrestrial civilizations. One of the most recent and important developments when it comes to the search for Dyson spheres is, or Dyson objects, is Project Hephaistos.
Project Hephaistos.
Project Hephaistos is a research effort focused on searching for potential Dyson candidates, and this project is documented in 2 peer-reviewed papers, Project Hephaistos I and Project Hephaistos II, each representing different phases of the work. Instead of looking for intentional signals like radio messages, Project Hephaistos analyzes data from various past astronomical observations to detect signatures like excess infrared radiation. So Project Hephaistos I analyzed around 5 million stars using data from the Gaia, WISE, and 2 master arrays, searching for infrared excess. While this phase of the project did not find any conclusive Dyson candidates, it established an important upper limit that no more than 1 in 100,000 stars could be hosting such structures. Building upon this, Project Hephaistos II applied a rule set with multiple selection criteria, and in the end, 7 late-stage M-class dwarf stars were identified as potential candidates.
Since the 7 candidates are all late-stage M-type stars, I'm going to explain a little bit about what those are and why that's significant. So late-stage Ms are red dwarfs. They're the coolest, least massive, and longest-lived stars in the main sequence. So they start like our sun, which is a G-type star. So they also have planetary systems like we do. And this stage M is much later in the stellar life cycle. So civilizations have more time to develop if they took birth around the time when the star was still a G-type star. So this time gives the civilizations an opportunity to advance from a type 0 to a type 2 civilization.
Okay, so going back to Project Hephaistos II and the selection pipeline they used. So in Project Hephaistos II, the team used a rule set consisting of both supervised and unsupervised learning techniques to identify potential Dyson objects among the data. So here's how the process worked. First, they collected the data on stars within 300 parsecs, which is about 978 light years, from the Gaia, 2MASS, and AllWise surveys. And they they focused on detections in the 12 and 22 micrometer infrared bands from WISE, which in WISE there are 4 different bands, W1, W2, W3, and W4, and these 2 bands are W3 and W4 from WISE. And then next, they applied a grid search to fit each star's data to the best Dyson object model, which they created, and they were trying to match the expected infrared signature. Then to improve candidate identification, they used advanced machine learning techniques. Specifically, they used a convolutional neural network to classify images, particularly to distinguish real signals from the background nebular regions or clouds of dust and gas. And why they did this is because these could cause false positives because of reflecting IR or emitting them. Afterwards, they carefully filtered out sources with a signal to noise ratio lower than 3.5 in the critical W3 and W4 infrared bands. And finally, each candidate went through a visual inspection of the mid-infrared and near-infrared images to exclude false positives and just verify the results from the machine learning.
Now, why are these Dyson candidates? So Project Hephaistos II came up with a rule set that decides that the strange brightnesses that these stars emit aren't just natural phenomenon and that we can truly call these Dyson candidates. So first off is the infrared excess. These stars give off a lot more heat, infrared light, than expected. And this could happen if something like a Dyson object is absorbing light and re-radiating it as heat. Next, the model match. So what this is that the project simulated, the researchers simulated what a star with a Dyson object around it might look like. And again, these 7 stars matched those models pretty well. So their light patterns fit the theory. Then they rejected natural causes. So they checked to make sure that these stars weren't young, and young stars are dusty and warm, but these stars don't show any signs of being young. So the brightness isn't just flickering, which often happens with young stars around like dust and clouds. And they also checked to make sure that there was no special hydrogen emission called hydrogen alpha. And hydrogen alpha emissions indicate regions where hydrogen is being ionized. And this is associated with star formation, or in other words, young stars. They also used AI to make sure that these aren't clouds of dust or background galaxies messing up the view. And after checking the stars with AI, they checked these 7 candidates specifically manually just to be sure. The researchers ensured that they were using high quality data only, since these stars had high signal strength in the important mid-infrared bands with a signal to noise ratio of 3.5. So these signals were reliable to use for data. Lastly, they made sure that the RU, which is renormalized unit weight, was less than 1.4, meaning that the star positions and movement are very precise, and there's no weirdness in how they move, like binary systems or something else. And binary systems are 2 stars that orbit around each other, which can also cause a fluctuation in brightness. So here, that's not the case. And finally, out of millions of stars, only 7 passed the rule set. And since they passed every test the researchers had for determining if it was a natural phenomenon, we know that these aren't natural phenomena that we already know of. This is why we can call these Dyson candidates. Here's a high-level overview of our steps, and I'll dive deeper in future slides. But we started out using NASA's Exoplanet archive dataset to gather a list of 38,000 observations. Then we took these 38,000 observations and plotted them using Orange, which is a no-code data mining software. And we plotted the magnitude of brightness variable versus the error in that measurement for 4 wise bands. After that, we identified the outliers on the graph and narrowed down to a list of just 83 stars to focus on. After that, we used conditional formatting for cells on an Excel. We color-coded values greater than, less than, between average, standard deviation, average plus or minus standard deviation. I'll elaborate more on this in a future slide. And this is where we are so far. Our next steps are determining which explanatory variables are important to make our rule set through the conditional formatting. And then after we have our own rule set on what makes a Dyson candidate, we're going to compare this rule set with the rule set that Project Hephaistos II found, and we're going to try to apply these on the 7 candidates that they found as well. now I'm gonna explain the step where we used orange. So in the picture in the top, you can see our setup on orange, and this allows us to just import a CSV with the first circle and then manipulate the data so that we end up with two variables, and we plotted that on a scatter plot. And you can see two examples below. So after we imported that CSV from NASA's Exoplanet archive that contained information about the stars, we looked at the outlier specifically. And the thought process behind this is that if we saw stars that have more error in brightness, this means that they're not just emitting a steady magnitude of brightness to us, and that brightness is changing, which causes that error. And these outliers, many of them could be Dyson candidates that don't emit this brightness at a steady pattern. These are the objects that we're looking for. This is why we looked at the outliers, and we end up with 83 stars. Examples of outliers is, if you look at the graph on the left, you'll see an oval. That's the confidence ellipse. So in that chunk right there, there's a circle, there's a dot at the top of the oval. That's an outlier. Then in the graph to the right, there's more dots that are outside the oval. Those are examples of outliers that we wanted to focus on. So we took these 83 stars that we wanted to focus on, we put those on an Excel sheet and did some conditional formatting. How we did this is everything yellow is between the average plus 1 standard deviation and average minus 1 standard deviation. Everything green is greater than average plus standard deviation, and everything red is average minus standard deviation, less than that. And you can see on the graph below, the graph on the bottom, the standard deviation graph, everything dark blue is essentially what we colored yellow. And the more yellow on a column means that we should focus on those variables more, because that'll help us find a rule set because the values for this variable are more clustered, as you can see on the graph. And if there's more red or green on a column, that means it's more of the stuff above and below the dark blue in the standard deviation chart. This means that these values are more spread out for that variable. That's not going to help us make the rule set. So after we figure out which columns are the most clustered, we're going to actually look at these variables and see, do they actually matter? And does it make sense to make a rule set? Just to make sure these aren't just spurious correlations. Our next steps, as I mentioned, we're going to identify which explanatory variables hold the greatest significance to make our new data set. We're also going to look into the recently released James Webb Hubble Telescope data and the upcoming Vera Rubin data release. This is going to be the latest, most accurate data. This is very important to our project. And then after we do the same process of using orange to plot it, using conditional formatting to figure out which variables matter for these new data sets, we're going to figure out we're going to make our own rule set on what makes a Dyson candidate, what the requirements are, and try to apply it to the 7 candidates Project Hephaistos II found for us, and compare our rule set with their rule set, hopefully adding on to it.
Future implications. So what would these results look like? A rule set or selection pipeline to identify potential candidates. It would mirror the logic of Project Hephaistos and potentially dredges up the Project Hephaistos candidates in addition to others that would need to be looked at. So how can science use this? It extends on Project Hephaistos II and helps others continue the search of more candidates. It gathers an intriguing set of stars that require for extraterrestrial life as the observations align with the descriptions of a Dyson object. These are all citations, all the websites we used. And thank you to our Professor Downing, Mr. Downing.
Golf clap, golf clap. Great, you guys. You've amazed everybody so much they don't have any questions. Oops.
Can you go back to the implications page?
Yeah, give me a second. Yeah.
Thank you.
Yeah, I see someone has their hand up. Go ahead, ask.
Can you go to the references page?
Yeah.
Any questions on these pages?
Thank you.
Yeah, Tyler, go ahead.
Oh yeah, this is just a random question, but how did you get access to the data from like Project Hephaistos and I mean, you said they're going to release further data from the James Webb Telescope and stuff as well. How are you going to get access from that or for that? Was it just on the web or like do you have to access it in a different way or just curious?
So the data that we used for this slideshow, that was the NASA's Exoplanet archive, right? If you look that up, there's places where you can just download CSVs. We use that. And then for the James Webb Hubble Telescope, which is what we're planning to use, and we're looking for that data set right now. What we've seen so far, I'm pretty sure if you, there's this thing called MAST. If you look up JWST, MAST, there's a place where you can put in searches or queries, and that gives you a list of stars. You can download that, and then we can use that for our project. Does that answer your question?
Yeah, that's great. Thank you.
Yeah, let me jump in real quick? Tyler, these data sets are just getting so massive that it doesn't make any sense to do anything but try and use APIs. Thanks.
Thank you very much.
Yeah.
Yeah, Abigail, go ahead.
Hi. I was wondering, why do you search for infrared radiation instead of like any other wavelength?
So the reason why we look at the infrared more than any other wavelength is because a Dyson object would absorb the light of its host star, and when it emits the energy, the most visible visible spectrum where you can notice the heat emissions is in the infrared range of the spectrum. So that's why we look more towards that when we're searching for Dyson objects in general.
Okay, thank you.
Or we go ahead.
Yeah, I actually had a question on the references. So, I was wondering, like, how did you have access to like the NASA Exoplanet archive? Was it like open to the public, or did you have to ask for like special recommendation or something? Or like permission?
If you look it up, it's open to the public. You can download CSVs from it.
All right, thank you.
Daksha?
Yeah. So I just had a question. You mentioned that you're going to be getting James Webb Telescope data soon. So do you predict like anything different? Like what do you predict with what will happen with that new data? Like do you expect to get like similar results fully or any significant changes?
Yeah, so we want to use the new data mainly because first of all, it's the latest, most accurate data because it's the most recent and it has more observations to it. It's like 1.5 terabytes of data. So that's why we want to use it. And also comparing it with what we have so far with the 38,000 observations that we were talking about, we hope to find mostly similar observations because that means that a process works. And we want to end up doing the process so that we can get the same 7 candidates that Project Hephaistos II got as well.
Yeah, thank you. And also, is the NASA Exoplanet archive one of your main references, or were there any other significant papers that you referred to for this project?
Sorry, can you repeat that?
Was the NASA Exoplanet archive like your main reference for the entire project throughout, or like what were like some significant papers that really helped you through the process?
So the main two papers that we, I guess, based our project off of were Project Hephaistos I and Project Hephaistos II. Our project is, I guess, going to compare like our rule set with what they have, and also we're going to test our rule set on the 7 candidates that they obtained after filtering out the data.
Okay, thank you. That was a great presentation.
Tanav, go ahead.
All right, so the whole objective behind this is to use science programming to try to discover if there's more life outside of Earth. That's what all I'm understanding here. Is that good? Is that good enough for understanding?
Kind of. I mean, we didn't really do any programming. We used Orange. It's a no-code software. And more than just finding life outside of Earth, that's a possibility because these are, again, Dyson candidates, which is a sign for life. But more than that, these stars are just, like, simply put, they're strange. There's when we were going through the slide that rules out some natural phenomenon, that shows that there's no natural phenomenon causing these stars to fluctuate in brightness and not even at a steady pattern that we know of right now. So we hope to extend on the 7 candidates and find a larger list of stars that are just interesting and that we need to figure out like what's going on behind them.
All right, so here's my new understanding. You're trying to use a no. Wait, was the no-code program again called what, Orange or something?
Orange
Awesome.
data mining. It's a widget-based integrated development environment for machine learning.
So you're trying to use Orange to discover a natural phenomenon involving the stars.
Not just discover the natural phenomenon behind the stars, more like find more stars that are like the 7 candidates that Project Hephaistos II found out. So we're kind of extending on that list.
Okay.
Okay. Allison?
So other than like NASA, which you said was a main source that you guys use to gather data, could you like list some other sources? And then looking at those data sets, how did you filter out like false positives when identifying Dyson sphere candidates?
Want me to take that?
Sure, if you want, yeah.
We used the data sets from NASA. That was a primary. A secondary, which was linked and had an intersection with the NASA data set, was from the European Space Agency. We've also looked at and discarded at one point or another data sets from Roscosmos and from the Japanese Space Agency. Filtering out false positives is done via the rule set. So that's, if you think back, this will be posted, you can look at this later, but in the description of the rule set, it gave you the limitations that identified exceptional behavior.
Okay, thank you.
Yeah. Any other advisors still on here, or?
Larry and I are
don't
still
wanna take
here.
all
I'm
the
gonna say,
time.
why don't we do one more question because we have 3 presenters tonight. We're gonna be here till 9 p.m. Let's go one
Can I
more.
also- and can they also send emails to just go ahead and send emails for your questions.
Yeah, if you have additional questions about the first presentation, what a hot star of a presentation, no pun intended. I saw the lightning across the sky.
You saw the light, huh? Machine learning.
I
I've been
did.
telling you for years.
Yeah,
You know, my brain is more scattered than the scatter plots.
you can start a thread in the student chat too on Google.
Yeah, go ahead. Those of you who still have questions, go ahead and dump your questions in the chat, and then we're going to move along to the second presenter just so that we can
Great
get
job.